Hi, and welcome to the presentation of Constraining Attacker Capabilities through Actuator Saturation. My name is Brian Finch, and I'm a master's student at Georgia Tech within the OMCS program. This is for the class Intro to Physical Security. So to start off with, this is not my own paper. This is a summarization and paraphrasing of an existing paper out there called Constraining Attacker Capabilities through Actuator Saturation. I do apologize if I improperly state the authors' names. The authors are as follows: Sahan Kafash, Jairo Giraldo, Carlos Morguia, Alvaro Cardenas, and Justin Roos. This paper was presented at the AACC, which is the Annual American Control Conference in 2018. The link to the paper can be seen in the presentation as well as the description below. The objectives and purpose of the paper is due to the current vulnerabilities and actuators that exist within our realm, as well as how we deal with them. So attackers and attacks can compromise the integrity and safety of systems if the actuators are set to dangerous states. Examples of some of these attacks can be seen in the Stuxnet, the 2016 breach of Ukrainian power grid, and attacks on modern cars, which is what this paper will go on to have a scenario of later. The solution that this paper provides is designing artificial limits on actuators that will constrict them from entering dangerous states that attackers might try to utilize. These limits are created via ellipsoidal bounds that do not sacrifice performance, but also do not overlap into dangerous states for actuators, which might be harmful to both the system and person and property around the system. A brief overview of what I'm going to explain is going to be the background of this paper, how to encapsulate an ellipsoidal bound, how to identify dangerous states, the case study given, the experiment given of the paper, as well as the results, and a brief conclusion. The background includes actuator attacks can be from direct manipulations of the actuators themselves, as well as manipulation of sensory data to affect the actuator. This was actually covered within the Intro to Physical Security class here at Georgia Tech for the online Masters in Computer Science, using the Modbus protocol and exploiting the old buffer overflow problem within that protocol. But that is not for this paper, but just to serve as an example of this actuator saturation problem. These attacks can result in undesired harmful effects on both the system and person and property around the system. The paper takes into account the set of reachable states and then applies artificial bounds. And these bounds applied are to constrain the harmful states without affecting the performance of the system or the goal of the system. The base equation utilized in order to get these constraints is the LTI discrete time system with individually bounded control inputs. LTI standing for the linear time invariant. To the left, bottom left, you can see the LTI equation, which is x of k plus 1 equals f times x of k plus g times use of k. X is the state, F is the state matrix, G is the input matrix, and use of K is the symmetrically bounded control input. The bottom right shows some of the limitations or the bounds that we will focus on for this paper. So how do we encapsulate an ellipsoidal bound? Our goal in the equation is to find the ellipsoid that encapsulates the entire reachable set of the system. To your right, you can see the following equation where x, as previously stated, is the state of the system which exists within the real domain. And this is evaluated over x transpose times p times x, which is less than or equal to alpha. P is a positively defined matrix, and alpha as well exists within the real, is a subset of all real numbers that are greater than 0. The paper goes on to explain what lemma 1 is, but lemma 1 and lemma 2 have the main difference of the constraint of less than or equal to m, which is already shown on the right, of v sub k plus 1 is less than or equal to alpha times v sub k plus the quantity of 1 minus alpha and quantity summarized over 1 to m of u sub k squared sub I over gamma I. The above equation, or the lemma 2 equation, can be translated to the following due to inequalities within the equation, which is v sub k is less than or equal to alpha v sub k minus 1 plus the quantity of 1 minus alpha n quantity times m. And combining both the lemma 2 and the translated equation, we get the following result of v sub k is less than or equal to alpha to the k minus 1 times v sub 1 plus the quantity of 1 minus alpha to the k minus 1 n quantity times m. And this equation is later utilized in order to create the actual ellipsoidal bound, or the set, of the following. So as you can still see, we still have the constraint of 1 to the m for all k's within the set of n, and we are utilizing the LTI equation as stated in the first. And we can get the following equation in order to get all of our actuator states, which can be seen, or actuator bounds, which can be seen in the R matrix, and the R matrix contains the eigenvalues that are the actuator bounds themselves. So, as it can be seen in the picture on the right side, the lower right side, the blue line is the line that identifies the entirety of the system set, which we have just solved for. Now, as you can see, there's a grayed out portion of this graph labeled D1. That's the dangerous set that has been identified through the equation above that allows the actuators to impose dangerous states within the system to the system itself or to those around the system or property around the system. As it can be seen, the equation is where the state of the system exists within the real numbers, and this is evaluated over the union of 1 to k of c sub I transpose times the state of the system, which must be greater than or equal to b sub I. So what this equation is saying is that the danger zone is the union of the half spaces defined by their boundary hyperplanes. And in order to avoid this, we need to apply this danger state to our calculation in order to have an ellipsoidal bound that does not intersect, cross, or contain the danger state itself. So the case study that this paper goes over is platooning. So what is platooning? Platooning is the idea of maintaining adequate distance between vehicles, such that changing the leader speed will not cause harmful results for those following. Some real-world examples of this is called ACC, or Adaptive Cruise Control. Another example is called CACC, which is Cooperative Adaptive Cruise Control. So in today's day, you can see that cars like Tesla, some Hondas will actually have ACC, Adaptive Cruise Control, where they sense the car in front of them and adapt their own cruise control in order to keep a set distance away from those in front of them. I'm not sure, but I believe Tesla is actually attempting to come out with CACC, or Cooperative Adaptive Cruise Control, which allows both cars, the car in front and the car behind, to communicate wirelessly with each other in order to identify car 1, who's the leader, is going at 60 kilometers an hour, and car 2 must also go at 60 kilometers an hour, but has to maintain a distance. So if car 1 says, I'm about to brake, car 2 says, I'm going to brake too, and therefore the caravan will essentially start, stop, accelerate, and deaccelerate at relatively the same speed. So let's set up our platooning experiment. The experiment can be seen on the right, which is an actual model of the platooning experiment, which has been defined previously outside of this paper but was brought up as the model itself. So these are the equations. This is the original equation, and we can sum it up down to this equation here, second to the bottom. The equation below it, which is use of I sub k, which can be seen here and here. So use of I sub k are actually the control variables within the model itself. And the reason that there are two values, use of I sub k itself plus w sub I sub k times d sub k comma v sub k, is that we are going to be both using adaptive cruise control and cooperatively adaptive cruise control. So the first one, underlined in green, is the adaptive cruise control. And the second one, underlined in yellow, is the cooperatively adaptive cruise control, or CACC. So going through the rest of the variables, k is the sampling instance, d is the distance, v is the speed, u, which we just went over, is the control input, delta t is the sampling period, and b is the velocity loss due to friction. Friction being from the road itself, as well as the air that is affecting the vehicle. So the experiment itself will contain 3 vehicles within the platoon, where d sub I asterisk is the desired distance. So we can change the model itself without affecting the outcome, where we have the d sub I sub k equals d sub I sub k minus d sub I asterisk, where, as you can see, d sub I sub k, if it equals 0, we know that the distance reached is what the desired distance is. Counter to this, if d sub I sub k equals negative d sub I asterisk, we know that a collision has occurred because the distance in between the two vehicles is essentially 0. Next, we have v asterisk, which is our desired velocity, and we change it in the same way we change distance, where v sub I sub k equals v sub I sub k minus v asterisk. With these, we can get our following states and matrices. The state set itself, which is quantified by both the new distance and the new velocity. We can also obtain our state matrix, which fits within our LTI equation that we went over at the beginning of this presentation. We can also get our G matrix, which is our input matrix that was also gone over in the beginning of this presentation. And lastly, we can see our symmetrically bounded control input, once again gone over in the beginning of this presentation. So let's continue with the simulated parameters, which are as follows. D, which is the desired distance here, is 1 meter. The desired velocity is 60 kilometers an hour. Our sample, delta t, is half a second. Our B sub I, which is our friction loss, is negative 0.1. Our K sub P sub I is 0.2. Our K sub D sub I is 0.3. And the acceleration of our 3 vehicles is 1.1, 0.9, and 1.05. Our resulting eigenvalues, or gamma, for creating an ellipsoidal constraint without constraining the dangerous state, can be seen as 1.2, 0.8, and 1.1. We're going to give the safety constraint as well, as we will be using it to go over in both the results of the experiment and the conclusion. So the eigenvalues after the danger zone has been identified, as well as the ellipsoidal has been constrained, is 0.03, 0.05, and 0.03 again. So using our first eigenvalues, we can see that the actuator can extend through the dotted blue line. This dotted blue line does include the danger space, even though it is not depicted on the graph. Excuse me. So the experiment run was at 25 seconds. The attacker was able to hack the CACC and start to inject code that'll change the actuators in order to change the distance in between the vehicles and cause a crash. As can be seen in the top right, at 25 seconds, a little bit after, you can see some drastic changes in D, as well as D1 and D2, which is the two vehicles that we're concerned about. As you can see at 0, at 39 seconds, D1 crosses the 0 path, which indicates that the two vehicles, vehicle 1 and 2, have crashed into each other because the distance, or the desired distance, is now equal to negative d sub I asterisk. Another indication of the attacker is the vehicle speed. You can see it starts to get out of control after that 25-second mark. So let's apply the new eigenvalues that will allow us to constrain the actuator so that even though the attacker attacks at 25 seconds, we don't see a negative impact to the system as well as to those around the system. So we are going to be applying the solid black line as the actuator ellipsoidal constraint. At 25 seconds, the attacker attacks. You do start to see a little bit change in the distance and some weird settling times thereafter. But you can still see that both D1 and D2, which is the distance between 1 and 2 and 2 and 3, do not cross that 0 threshold, which indicate that there is no collision between the vehicles. As well as you can see in the vehicle speed, there is some change after 25 seconds, but overall you maintain that stability throughout the system. So the conclusion in this is bounding the actuators is helpful for us to reach a safe set of states that will be resilient to attackers and unstable to the system. These bounds might come at a cost of conventional performance metrics, which was stated within the paper itself, but will be analyzed in future works to come. I do appreciate the opportunity to be able to summarize this paper, and if you have any questions, please leave them both in the comments below or in the Piazza post, which this will be associated with. Thank you very much for your time. Have a nice day.